In this video, we want to demonstrate how to resolve simplex linear programming problems using the simplex method. In our previous video, we were able to show how to resolve LP problems using the graphical approach. So we want to scale up a little to show how, demonstrate how we can use simplex method or approach to resolve a simplex linear programming problem. The case at hand is a situation where we want to find out the right combination of the products, for say the manufacturer, and he is interested in maximizing, optimizing his profit. And we have this objective function here, which is to maximize profit 30x1 plus 20x2. We have our set of structural constraints and of course the non-negativity constraints, which we have been able to explain in details in our previous videos. Kindly refer to those videos if you do not understand, if you do not uh, understand the structure properly. So now we want to look at how to begin with setting out the program proper. And the first thing we do is to standardize the model. As we can see, we have all of them to be less than or equal to sign inequalities, and that goes to tell us how to modify the model and standardize it. So, solution. We'll have one to put it in standard form. What we mean by standardizing it, putting it in standard form, is just to find a way to create a balance between the right hand side and the left hand side. Given the fact that we have less than or equal to type inequalities for the three constraints, we'll be finding a way to balance the right hand side and the left hand side. By explanation, it simply means that since this side, the left hand side, mean the input output ratio, for instance, for us to make 1 unit of a product X1, 3 units of this resource will go into it, and 2 units of this resource will go into the production of 1 unit of X2. So, by the virtue of fact that we have less than or equal to type here, it simply means that we may not be able to use up this resource available here. So, for us to standardize, which literally means to find a way to balance the two sides, we will be bringing in something to represent that part that may not be used up. So, unused resources in operations research, quantitative techniques is known as slack. It's labeled slack. So, because for the fact that we may not be able to use up the whole of the left hand side in this production plan that we have, we are going to bring in something that will represent that part that may not be used, and whichever one that will bring in will label it. And the same explanation goes to this because it's of the same type of a inequality sign. So we bring in, firstly, maximize our P, which is profit, 30x1 plus 20x2, subject to our three x1 plus 2x2. Now, before we can say that the two sides are equal, we're going to bring in something that will represent that part that may not be used, which we'll call slack, represented by letter S, which is S. We can now, having added this, we can now assume that the two sides are equal, now equal to 900. Then, for the fact that we may have another S for another constraint equation, so we're going to label this, we're going to give this one a label. So it is now slack number 1, that is S1. Now, same modification goes for this. We're bringing artificial variables to balance it. So we have 2x1 plus 2x2 less than or equal to 600. So I have 2x1 plus 2x2 then plus s number 2, that is representing this, will now be equal to 600. Now, the third one is 30x1 plus 15x2 will be less than or equal to 6,000. So we're bringing in the next one, which is S3, and now we'll make it equal to 6,000. So we've been able to bring in our artificial variables that will represent that part of the resource available that may not go into the program proper. So that is why we have S1 to represent the structural constraint, S2 second constraint, S3 the third constraint. So having done that, the next thing will now be to balance it up for the purpose of symmetry. So as you can see, if I bring in plus 0s1 here, I have not added anything here because 0 by s1 will give me the same thing, 0. Plus 0s1 here, nothing has been added, plus 0s2 plus 0s2, then plus 0s3 plus 0s3, such that the program will be able to run. Now, all the artificial variables that you have introduced by rule must be represented in the objective function, and their coefficients, of course. For x1, the coefficient of x1 is 30, which means if you produce 1 unit of x1, the profit will be 30 naira. If you produce 1 unit of x2, the profit will be 20 naira. So all the artificial variables introduced must be represented in a objective function. And their coefficient will be 0. Of course, it's very clear because they won't be adding anything, in real terms to us. So if we bring in s1 to the objective function, we have plus 0s1 plus 0s2 plus 0s3. Now, having brought in the artificial variables in the objective function, the next thing will now be to bring in our non-negativity constraint, which is everything that we have: 1, x1, x2, s1, s2, s3. Everything must be greater than or equal to 0. Now, this is how we have standardized our program, our model. So the next thing will now be to build our basic feasible solution, the BFS, which is akin to a situation of a zero production. Then from there, we'll now begin to iterate and iterate to get to the point of optimality. So we are going to clean up this place and use it to build our basic feasible solution. So we have for our basic feasible solution, which we've mentioned earlier that is close to just more like a point of zero production, it is not expected to be optimal. So what do we have? The components are simple. We have our basis or basic variable. We have our contribution represented by CB. We have our quantity column. Then we can now bring in our variables x1, x2, s1, s2, s3, and of course replacement quantity. So our CJ will be the coefficients, which is 30, 20, 0, 0, 0. Now, for the basic variables, which we have mentioned, that is a point of zero production. So what we're going to have in the basis are the variables, artificial variables, to represent the constraints that we want to manipulate. In essence, what we're doing is to find a way of solving the structural constraints simultaneously for us to be able to achieve our objectives here. So for at the basis, at the point of zero productions, if we multiply others, and equate them to zero, we have only s1 will be equal to 900. So for the first one, we have s1 to represent structural equation 1, equation 2, and 3. Our structural constraint 1, 2, and 3. So we have s1, s2, and s3 as zero production level, s3. Of course, their contribution is 0, 0, and 0. And the associated capacity availability, the resource availability will be 900, 600, and 6,000. Now, the input-output ratio will now come in. For x1, we have 3, 2, and 30. 3, 2, 30. For x2, we have 2, 2, 15. 2, 2, 1, 5, 15. Then we have 1, 0, 0 for s1. 1, 0, 0. For s2, we have 0, 1, 0. Have 0, 1, 0. And for s3, we have 0, 0, 1, 0, 0, 1. So the next thing will now be to find out whether this solution has solved our problem, whether we've attained optimality. So what do? We first of all compute the CJ minus ZJ column, which is more like a gross profit column, then with which we are going to compute our we're going to compute our ZJ column, which is more like a gross profit column, with which we will now compute our CJ minus ZJ column, which is our net evaluation rule, where we are going to determine whether we have attained optimality or not. So how do we now compute our ZJ column? Very simple. For the input-output ratios, it will now be 3 multiplied by the contribution plus this 2 multiplied by the contribution plus 30 multiplied by the contribution. That will give me the ZJ value for x1. So the ZJ for x1. So I will quickly just clean here and use it for our computation, and I'll bring them in. So for our ZJ x1, so computation of ZJ values. For ZJX1, we are going to have 3 by 0 plus 2 by 0 plus 30 by 0, which gives us a 0. So ZJX1 will be 0. For X2, we have 2 by 0, 2 by 0, 15 by 0. So we have 2, 0 plus 2, 0 plus 15 by 0. It gives us 0. So I'll have 0 here. Then 1 times 0, 0 by 0, 0 by 0. For S1, let's just do this one. S1, which is 1 by 0 plus 0 by 0 plus 0 by 0. Of course, we'll have a 0. So here will be 0. And for S2, we have 0, 1, 0. So we have 0 by 0 plus 1 by 0 plus 0 by 0, which is also 0. The last one, S3, we have 0 by 0 plus 0 by 0 plus 1 by 0. So everything comes back to 0. So we have 0 here, 0 here. So that is how to compute our ZJ values. So the next computation we're going to have, which is our CJ minus the ZJ, which you also call the net evaluation rule. So the CJ minus ZJ NER, net evaluation rule, will now be, these are our CJ values, which we've mentioned earlier that they are our coefficients. So for this is just 30 minus the corresponding ZJ value, which is 0. So 30 minus 0 will give me 30. 20 minus 0 will give me 20. 0 minus 0 will have 0. 0 minus 0 will have 0. And this minus this will have 0. So these are basic feasible solution, the BFS, which we have mentioned earlier, that expectedly it shouldn't produce optimal solution. So we are going to now look at this and find out what next to do. Now, for a simplex maximization case, you attain optimality when all the values in the net evaluation rule are either negative or 0. What it simply means is that if you have positive values here, you still have the potential, they still have the potential of improving on your profits. But once you have negative values, any non-basic variable that we introduce into the basis will reduce the profit potentials, and any non-basic variable that has with negative sign, any negative non-basic variable that you introduce into the basis will reduce it, and the one that has zero values will leave the values, the profit standing, unchanged. So clearly, for maximization case, the solution becomes optimal when all the values in Cj minus Zj, that is the net evaluation rule, are either negative or zero. So by simple inspection, we can see that we still have positive values, which means that the introducing this x1 into the basis has the potential of improving our profit standing, and introducing x2 into our basis, because it still has this positive value, has the potential of improving our profit standing. So we have not attained optimality at this point. So the next thing will be to find a way to improve on the position at this point. So we are going to transform. We're going to transform to be able to improve on what we have now. So the first thing in improving on the BFS, or what we have, will be to determine the value, the variable that will leave, that will go into the basis. The first thing will be to determine the variable that will go into the basis, then with which we will now determine the basic variable that will also leave the basis. Because what it is at this point, we have 1, 2, 3 representing the constraint equations, and continually we'll keep having 3 of them here. So we are going to determine the non-basic variable. At this point, we have x1, x2, x1, x2. So any one that is not here presently is termed non-basic. Those that are already in the basis, those are already programmed, the program are called basic variables. So now, having seen that, we have only s1, s2, s3, being represented in the basis. So we want to find out which one leaves, which one comes in. So by a very simple explanation, we choose the incoming variable, the one that will come in by inspection, by visual inspection. Because we have a maximization case, what these values stand for, what they mean is that the introduction of any of them will increase the profit standing by that proportion. So what we're going to do is to find out, to look at this and say which one is higher, which one is going to give us more profit if it is introduced in the basis. And of course, profit is about higher values. So we have 30, we have 20. So in maximization case, you select the one that has the variable, the non-basic variable that has the highest positive values to come into the basis. So we have x1 to be 30, x2 20. So automatically we're going to have x1 to come in, and we call this the incoming variable, pivot variable, key variable, or colon. Okay, having determined what the variable that will come in, we'll now use this variable to determine the one that will go out of the basis. And it's a very simple computation. So we compute the replacement quantity, which is This, the quantities associated to the constraint multiplied by the associated values, the corresponding values in the incoming variable. So for S1, we'll be dividing 900 by 3. For S2, it will be 600 by 2. And for S3, it will be 6000 by 30. So we'll have 900 divided by 3, which will give me this will have 300. Then 600 divided by 2 will have this goes, we have also 300. And 6000 divided by 30, which is 6000 by 30. We have this, this goes 1, it goes 2, so which will have 200. So we have 300, 300, 200. And the rule is that any variable in the basis that has the least non-negative replacement quantity will be the one to leave our basis. By a simple explanation, it shows that its ratio, of improvement is less than its capacity to improve is less than what others are offering us. So we are going to remove S3, which is the one that has a least positive replacement quantity. So we're going to have this go. So we label this outgoing variable pivot row or key row. Alright, so in the process of choosing the incoming and outgoing variable, there are values that are very important to us, especially one. The value that lies at the intersection of the outgoing variable and the incoming variable is very important to us because it will be made use of when we make transformations that we're going to see shortly. So at the intersection of incoming and outgoing variable, we have 30, which we call the key number, pivot number. So we're going to make use of this. So having determined all these things, we're now going to design our next solution. We're going to improve on what we have at this point. So the next one will be labeled the first solution, which we're going to have our BV to stand for basic variable. BV contribution colon quantity, then we have x1, x2, x3, so x2, s1, s2, s3 are q, which are replacement quantity. Then the CJ values, which are the coefficients 30, 20, 0, 0, 0. Now we're going to bring in our values. So the first thing we do in improving our solution, moving from BFS 2 of the first solution would be to determine the transform. We have decided that x1 should be retained and the contribution is 0. S2 should also be retained with a contribution of 0. Then S3 should leave the basis, which is the outgoing variable. S3 should leave the basis and its position be taken by x1. So we now have x1 here, and the coefficient, which is the contribution, is of course 30. So all other values that will come back into the program will be improved on. That is what we mean by transformation. Simply, they will be improved on. So we are going to use a very simple formula to improve them. So the rule guiding the transformation of a key row is different from the rule guiding the transformation of non-key rows. So the first thing we're going to do is to transform the key row, which is a S3. It's S3. So for us to transform our key row, the rule says divide all the entries, all the values in that key row by the key number, which means we'll be dividing all the values from here, 6,000 by 30, 30 by itself, 15 by 30, all through to produce the transformed entries in the in the key row. So let me put it here. So transformation of key row S3. Key row transformation will be for 6,000, we have 6,000 divided by 30. We have is equal to this 3 by 6, we have 2, so we have 200. Then 30 by itself will give us 1. 30 by 30 equal to 1. So this place will be 1. 15 by 30 will give us 1 over 5. 15 by 30 equals 1 over 5. So we'll have 1 over 2. It was 1 over 2. So we'll have 1 over 2. Then 0 by 30 will give us 0. 0 by 30 will give us 0. So this place will be 0. 0 by 30 again, we'll have 0. Then 1 by 30, we'll have 1 over 30. So that is how to transform our key row. So we have been able to transform all the entries in the key row. So the next will be to transform our non-key rows, and we'll have a separate formula, a very interesting formula that we use to transform the non-key rows. So we have that the old row number minus the corresponding number in the key row multiplied by the fixed ratio, which is the ratio of exchange, will give us the new row number. So the first thing we do when we want to transform non-key rows will be to determine what is our fixed ratio, the ratio of exchange. Very simple. For any row that is to be transformed, for any non-key row that is to be transformed, the fixed ratio is determined by the value, the corresponding value in the key row divided by the key number, such that if we want to transform S1, the fixed ratio will be 3 divided by 30, because the row we are transforming is S1 and the value corresponding to it is 3. Then if we want to transform S2, the fixed ratio will be 2 divided by 30. That is the ratio of exchange. So for our FR, which is our fixed ratio, S1 will be equal to 3 divided by 30, which gives us 1/10. Now, having gotten our fixed ratio, we'll now apply this formula proper. So our old row number are the values, the entries that we want to transform. Now that our focus is on S1, so the first value we're going to transform is this quantity value, which is 900. So if we have 900, the number that corresponds to 900 in the key row, this is corresponding number in the key row. This is 900 and the corresponding value here is 6,000. So we have 6,000 multiplied by the fixed ratio that we have determined to be 1/10. This will give me the new row number, which is going to replace it. So let's just work it out. So we have 900 by this and this. So we have this goes. So we have 900 minus 600. So we're going to have 300. So which is simply means that 900, the position of 900, 300 should take. So we have 300. Then let's quickly transform this. 3. We have 3 minus. The corresponding number to 3 is 30. So the key row is 30. Multiplied by 1/10. That will give me the new number. So this goes. So I have 3 minus 3, which is 0. So in place of this 3, 0 comes in. I have 0. Now we have to transform these two. So we have 2 minus. The corresponding value is 15. 15 multiplied by 1/10. We have, what do we have? We have 0. 5 goes, this is 5 goes is 2. 5 goes is 3. So we have 2 minus 3/2. Let's just expand it here. So 2 minus 3. 3 by 1 is 3. And 2 by 1 is 2. So 3/2. So that we're going to have 2 minus 3. 2/1 minus 3/2. So take the LCM to be 2. 1 by 2 will give us 2. 2 times 2 is 4. Take 2 by 1 by 2 is 1. 1 times 3 is 3, which is 3 here. So that we're going to have 1/2. 4 minus 3 is 1. So we are going to have 1/2. So this will be, we have transformed 3. So this is going to be 1/2. So the next will be to transform 1. So one transformation of 1 will be 1 by 1 by 1 minus corresponding value to 1 is 0 multiplied by 1 over 10. So the product of this is 0, so 1 minus this, so we're going to have 1. So 1 should come back here. So the next thing will be to transform this 0. So let me clean up this. The next will be to transform this 0. So 0 minus the product of 0 by 1 over 3, 1 over 10. 1 over 10 will give me 0. So everything will come back to 0. And the last one there will be to transform this 0. And the corresponding value is 1. So we have 0 minus 1 multiplied by 1 over 10. So we're going to have this cancelled. So we're going to have minus 1 over 10. We have minus 1 over 10. So that's how to transform non-basic, non-pivot rules. So we're going to use that same method and that same formula to transform quickly S2 and reevaluate. So the first thing we're going to do is to determine our fixed ratio for transformation of row S2. And it has been said that earlier that it is the corresponding value in the key column divided by the key number. So for S2 transformation, the fixed ratio will be 2 divided by 30, which is S2 fixed ratio S2 will be equal to 2 divided by 30. It gives us 1 over 15. So we're going to use 1 over 15 to transform our row S2. So start by transforming this quantity 600. So 600 minus the corresponding value to 600 is 6,000. So we have 6,000 multiplied by 1 over 15. What do we have? We have 15 here, gives us 1. 15 here gives us 4. So we have 600 minus 400. That gives me 200. So we have 200 here. Then the next will be to transform these 2, which is 2 minus the corresponding value is 30, which is 30 here, multiplied by 1 over 15. So this goes 1, this goes 2. 2 minus itself 2 will have 0. So we'll have 0 here. Now the next one will be this to transform this 15. 15 minus the product of to transform these 2, which is 2 minus the associated value, the corresponding value is 15. So we have 15 multiply by 1 over 15. What do we have? So 15 by itself will have 1. So 2 minus 1 will have 1. Alright, so we're going to have 1 here. So the next will be to transform the 0. So have 0 minus the corresponding value is a 0. So have 0 by 1 over 15. It gives me 0. So I'll have 0 here. Then the next will be to transform this 1, which will be 1 minus the corresponding value is 0. 0 have 0 multiplied by 1 over 15. So we're going to have the product of these brackets will be 0. So we're going to have 1. So 1 comes in here. So can put it up this and complete the last one. So the next will be to transform this, which is 0 minus the corresponding value is 1. 1 multiplied by 1 over 15. So this will give us minus 1 over 15. That should come in here. 1 over 15. Negative 1 over 15. Now, having transformed all the values, having improved on all the values, we're now going to test again, go for test for optimality to find out if we have attained optimality and determined the right production combination plan that will satisfy this condition. So we're going to quickly do our ZJ column, which we have shown how to do, which is this by this, this by this, this by this plus this by this plus this by this, and this by this, this by this. Okay, so now our ZJ value will be for x1 0 by 0 plus 0 by 0 plus 1 by 30 will give me 30. This by this 0, this by this 0, 1 over 2 multiplied by this is 30 multiplied by 1 over 2, which is 30 divided by 2, which means we're going to have 15. So we'll have 15. Then this times this is 0, this times this is 0, this times this is also 0. So we'll have 0. This by this 0, this by this 0, this by this 0, we'll have a 0. Then this by this 0, this by this 0, this by this will now be 30 multiplied by 1 over 30. So we're going to have 30 goes 1, 30 goes 1. So we're going to have a 1. So having done this, the next task will be to determine our CJ minus ZJ, which is our next evaluation rule. CJ minus ZJ, which is our NER, our net evaluation rule, where we check to determine whether we have attained optimality or not. So 30 minus 30 will give me 0. 20 minus 15 will give me 5. 0 minus 0, 0, 0, 0 minus 1 will give me minus 1. So this is our net evaluation rule for the first solution. So we have established that our our the guide is you attain optimality for a simplex maximization problem when all the values in the net evaluation row are either negative or zero. Because we are maximizing, anytime we still have positive value in the net evaluation row, it is a pointer, it's an indication that the solution can be improved. So we still have a possibility of improving on our solution. So we are going to also improve on this. We're going to revise this solution to improve on it. And it's going to be called our second solution. So quickly, we're going to do that. We're going to do that quickly by our established rules, the transformations, the incoming variable rule, the outgoing variable rule. We're going to quickly do that. So now the first assignment will be to determine our incoming variable and outgoing variable. And to determine our incoming variable, it is done by visual inspection. So as we can see, we have -1, 0, 0, 0, 0.5, +5, and 0, which means that anyone we introduce from this will improve on our profit potentials. So we have 5, that is why we are going to select x2 to be our incoming variable. Then we'll now use the incoming variable determined to compute for the outgoing variable, which is by dividing the quantity column by the associated values in the column of in the key column. So we have 300 divided by 1/2, that is by half, 200 by 1, 200 by half. And the rule says the RQ, the replacement quantity that has the least non-negative, the variable that has a least non-negative the replacement quantity would be the one that comes into the basis. So we are going to determine that and use it to design our next program. So it's now 300 divided by 1/2, 300 by 1/2, 300 divided by 1/2, and that will give me 300/1 multiplied by divided by 1/2, which means that we have 300/1 multiplied by 2/1, which gives me 600. So here we have 600. And the next one for S2 is 200 divided by 1, which is 200/1, which means we're going to have 200. Is 200. So, and the next one will be 200 divided by 1/2, which of course will give me 400. So don't forget, who says the outgoing variable will be the one that has the least non-negative replacement quantity. So our replacement quantity that is the least is 200. 200. So which is for structural constraints XS2, which is going to leave us. And this position will be taken by X2. So we'll now use it to design our next solution and see what is going to turn out. So we have BV, this is the basic variable, CV, the quantity column. We have X1, X2, S1, S3, sorry, S2, S3. and our replacement quantity. So we're going to have our CJ values, which is the coefficients. We have 30, 20, 0, 0, and 0. So we have determined that S1 remains with its coefficient of 0. S1, the coefficient is 0, and S2, the position of S2 will be taken by X2. So we have X2 to take the position of S2, and the coefficient is 20. We have 20, and X1 comes back. So we have X1, so the coefficient is 30. So the next thing now will now be to embark on our transformation quickly, to transform quickly and re-evaluate. So the first transformation that should be done is to transform the key row. And the rule for transformation of the key row is to divide all the values, all the entries in the key row by the key number. Now, the key number is the value that lies at the intersection of the key row and the key column. So, key column and row. So, we have 1 here. This is our key number by 1 here. So, we're going to divide all the entries in S2 by 1. So, 200 divided by 1 will be 200. 0 divided by 1 will be 0. 1 by itself, 1. 0 by 1, 0. 1 by 1, 1. And 1, negative 1 over 15 is definitely negative 1 over 15. So we're going to have minus 1 over 15. Now, the next will be to transform our non-key rows. And the rule for transformation of non-key rows we have established is very simple. So it is old row number minus the corresponding value, the corresponding number in the key column multiplied by the fixed ratio will give us the new row number. So the first thing we're going to do will be to determine the fixed ratio. So the fixed ratio for transformation of S1 will be the value that corresponds to S1 in the key column divided by the key number. So for S1 transformation, the formula will remain that old row number minus the corresponding number in the key row multiplied by the fixed ratio will give me the new row number. So for S1, fixed ratio S1 will be equal to 1 over 2 divided by 1. 1 over 2 divided by 1, which is equal to 1 over 2 multiplied by 1 over 1, which brings it back to 1 over 2. So, having determined our fixed ratio, we can now get into the transformation proper. So, to transform our this 300, which is our positive value for S1, we're going to have the old row number, which is the 300, minus the corresponding value to this in the key column is 200. in the key row is 200. This corresponds to this to this to this. So 300 corresponds to 200. So I'm going to have 200 here multiplied by the fixed ratio, which is 1 over 2. Whatever we have will be our new row number. So this is 2. 2 goes to this is 1. 2 goes to this is also 1. So 300 minus 300 minus 100 will give me 200. So in place of this 300, 200 should take. Now the next will be to transform 0. So have 0 minus the corresponding value to this 0 is also 0. So have 0 multiplied by the fixed ratio, which is 1 over 2. And this will give me all 0. The product is 0, is 0. So I'm going to have 0. Now, the next will be to transform this half 1 over 2. So 1 over 2 minus the corresponding value to 1 over 2 is 1. 1 multiplied by 1 over 2. So 1 times 1 over 2 is 1 over 2. 1 over 2 minus itself will give me 0. So I have here to be 0. So the next will be to transform 1 by the same value, by the same formula. So we're going to have 1 minus the corresponding value to 1 in the key column, in the key rows rather, is 0. So we're going to have 0 multiplied by 1 over 2. So the product of these brackets, what comes out of the bracket is 0. So 1 minus this will give me 1. I have 1. So this place will be 1. So the next will be to transform this 0, which I can quickly do here. So 0 minus the corresponding value to the 0 is 1, which I have 1 multiplied by 1 over 2. So I'm going to have this is equal to minus 1 over 2, because the product of this is 1 over 2. If negative opposite, we have minus 1 over 2. So we have here to be minus 1 over 2. So the last on that row rather will be to transform minus 1 over 10, which I have minus 1 over 10 minus the corresponding value. The corresponding value is minus 1 over 15. This minus 1 over 15 multiplied by the fixed ratio, which is 1 over 2. So we can quickly expand this. This will be minus 1 over 10 minus 1 minus 1 multiplied by 1 give me minus 1 over 15 times 2 will give me 30. So open the bracket. It gives me minus 1 over 10 minus this by this will give me plus 1 over 30. Plus 1 over 30. So we're going to have take the LCM, which is 30. 10 by 30 will give us 3. 3 by minus 1 give me minus 3. then plus 30 by itself is 1. 1 times 1 is also 1. So have, this give me minus 2 over 30. So that I'll have 2, 1, 2 by this 15. So I have minus 1 over 15. So I'll have here minus 1 over 15. So we've been able to successfully transformed row S1. So the next thing now will be to transform row S2. So row row X1 here, we'll be able to transform S1. So we're going to transform row X1, then after which we'll now recompute to check if we'll be able to attain optimality. So the first thing for us to do is to determine our fixed ratio for transformation of X1. So our fixed ratio X1 will be 1 over 2, which is the value corresponding to the row we are transforming, divided by the key number. So 1 over 2 divided by 1. 1 over 2 divided by 1 will give me 1 over 2. So with that, we'll now recompute. We'll now transform our X1. So fixed ratio S1 is equal to 1 over 2. So for transformation of X1, we start from the quantity, which is 200. First one is 200 minus the corresponding value to 200 is 200 in the key row. This is 200. This corresponds to 200. 1, 0 corresponds to it. 1 over 2, 1 corresponds to it. So 200, the corresponding value is also 200 multiplied by 1 over 2. So what do we have? We're going to have this goes, we have 1. So 200 minus 100 will give us 100. So in our new table, the position of 200, 100 should take. Now the next will be to transform 1. Transform 1. 1 minus the corresponding value to 1. Corresponding value to 1 is 0 multiplied by 1 over 2. The product of this is 0, so we have 1. So this place becomes 1. Then the next will be to transform we should have transformed this 0 first. So this place is we're going to transform 0 first. So this first. So we're going to have 0 minus 0, the corresponding number. So sorry there for that mix up. The transformation is on 1. So I have 1 minus 0, 0 multiplied by 1 over 2, which is 1. So sorry, this one is correct. Now the next value to be transformed is 1 over 2, and the corresponding value is 1. So 1 over 2 minus 1 multiplied by 1 over 2, because the corresponding value to this is 1. So we're going to have Product of this is a half. So 1 over 2 minus 1 over 2, we're going to have 0. So this place becomes 0. Then the next will be to transform this 0. Now we have 0 minus 1 because this 0 corresponds to this 0. So we're going to transform that first. So 0, the corresponding value is 0, multiplied by 1 over 2. We're going to have 0. So this place becomes 0. Then we transform this 0 that corresponds to 1. So we have 0 minus 1 multiplied by 1 over 2, which 1 times 1 over 2 will give me 1 over 2. Negative opposite will have minus 1 over 2. So I'm going to have minus 1 over 2. Then the last but not the least will be to transform 1 over 30. So we have 1 over 30 minus the corresponding value to 1 over 30 is minus 1 over 15. So we have 1 negative 1 over 15 multiplied by 1 over 2. What do we have? So if we expand this, we have 1 over 30 minus 1 times minus 1 will give me minus 1 over 15 times 2 will give 30, such that we have by expansion 1 over 30 minus, okay, negative opposite this, we have 1 over 30 plus 1 over 30. Is that correct? 1 over 30. Okay, so okay, so we're going to have is equals to this. We have 30, 1 by this, we have 30 by itself, we have 1 times this will have 1 plus 30 by itself 1 into this will have 1, so we're going to have 2 over 30 that gives us 1 over 15. So we're going to have 1 over 15. So having dealt with our transformations proper, the next thing will now be to actually look at our Cj minus Zj, to find out if we've attained optimality or not. So the next thing will be to compute our Zj values. So we're going to have our Zj, and for Zj x1 is this by this 0, this by this 0, 1 by 30, 30. For x2 is 0 times 0, 0, 1 times 20, 0, 0 times 30, 0. Sorry, 1 times 20, 20, so we're going to have 20. Then for s1, 1 by 0, 0, 0 by this 0, 0 by this, we're going to have 0. Then for s1, this by this is 0, 1 times 20 plus minus 1 over 2 times 30. So we're going to expand that, we're going to work that out. 1 by 20 plus minus 1 over 2 by 30. So we're going to work out what we have in here. So we have 20 plus minus 1 times 30 is 30 divided by 2, which will have minus 30 over 2. So we have 20 plus minus 15 over 1 minus 15 minus 15. So we have 20 minus 15. It gives us a 5. So we're going to have 5 here. Then the next will be this by this is 0. This by this is 20 by minus 1 over 15 plus 30 by 1 over 15. So we're going to have minus 20 over 15 plus 30 over 15. So we're going to have take LCM, which is 15. And now have 15 by itself is 1 times minus 20 is minus 20. Minus this is plus 30. And this comes down to minus 20 plus 30 will give us 10. Positive 10. This is equal to 10 over 15. And we'll now have 5 goes, we have 2. 5 goes, we have 3. So this will come down to 2 over 3. So we're going to have 2 over 3. So that completes the computation of the ZJ values for this iteration. So the next thing, of course, this is our second solution. This is now our second solution coming from the first solution. This is our second solution. So the next will now be to clean up this and compute our NER, the net evaluation row, where we will now assess to determine whether we've attained optimality or not. So, okay, so having computed our ZJ values, the next will be to look at our CJ minus ZJ row. That is the net evaluation row to know whether we've attained optimality or not. So our CJ minus ZJ, known as our net evaluation row, will be 30 for x1. 30 minus 30 we have 0. 20 minus 20, 0. 0 minus itself, 0. 0 minus 5, minus 5. 0 minus 1 over 2 over 3, we have negative 2 over 3. Alright, recall that the rule says that you attain optimality for a simplex maximization case when all the values in the net evaluation row are either negative or 0. So by inspection, by evaluation of the values, the entries in how we have in our net evaluation row, we have 0, 0, 0, minus 5, minus 1, 2 over 3, which simply means that we do not have any positive value there, and that suggests that we've attained optimality. So, having attained optimality, what's our decision? What's the product combination that will yield the highest profit? So, we are going to run this. So, the program has told us that the best combination of the production plan will be to produce 200 units of X2 and 100 units of X1. So optimal combination will be X2 200, X1 100. And our maximum profit, the optimal profit, will be to substitute these values into the objective function. And the objective function is to maximize profit, which is 30 by x1, 30 by x1 plus 20 x2. So if we substitute, we have 30 by x1, which is 100, plus 20 by x2, which is 200. So we're going to have 3000 plus 4000, which equates to 7000 naira. So using the simplex approach or method to resolve the problem, we'll have that the optimal combination will be to produce 200 units of product X1 and 200 units of product X2 and 100 units of product X1, and our maximum production plan will yield 7,000 naira as a profit. Thank you. We hope that you find this relevant. See you in our next video. Bye.